This video is for my Algebra 1 class. It is over lesson 37 using scientific notation. Ladies and gentlemen, scientific notation is a way of rewriting a number as a times 10 to the power of n, where 1 is less than or equal to a, but less than 10, and n is an integer. So, ladies and gentlemen, there are two parts to scientific notation that we see here in the definition. So the first part, a, is sometimes called the coefficient. So just like the coefficient of a variable term, it's the number being multiplied out front. This is the number being multiplied out front, not of a variable, but of the second part, which is our power of 10. So you'll notice here that a and n are both written as variables, but 10 is a number. 10 will always be 10. Now a, to try to describe a hopefully in a few more terms, the coefficient here we see is 1 is less than or equal to a. In other words, a is greater than or equal to 1. So what that means is that it cannot be less than 1. A cannot be less than 1. If you think about it, if it was less than 1, then the whole number part of that would be 0. So we're saying it can't be 0. It's got to be something other than 0. But however, saying that a is less than 10 means that that whole number part cannot be a double digit. So essentially what this is telling us is that we have one whole number, and we're using whole number as a single adjective, so we give it a hyphen. We have one whole number digit. So if you look at the whole number place values, there's only going to be one digit there. So 2.7, 3.149. Those would all have a single whole number digit. The power of 10 then is going to be 10 to some power, and that power, n, has to be an integer. So remember that the integers include 0. They include the counting numbers, and they also include the opposites of the counting numbers. So ladies and gentlemen, let's try this out then. 2, 5, 0, 0, comma, and then let's put 6 more zeros after that. So scientific notation, first of all, we typically use this with very large numbers. In science, sometimes we have very large numbers, especially when you're looking at space. There are very large objects in space, and they have very large distances between them. So if I were to rewrite this in scientific notation, I want my coefficient to be some number where there's just a single whole number digit. So essentially what you're going to do is you're going to take the decimal here and you're going to slide it over. So if I slide it over, do we have a single whole number digit? Absolutely not. Slide it over a few more spaces, I'll put it right there. Do I have a single whole number digit? No. I'd have 4 whole number digits. 3, 2 whole number digits, 1. So if we put the decimal right here, we'd have 2.5 and then a bunch of zeros, which really is just 2.5. So 2.5 is the a here. It's the coefficient. Now times 10 to the power of n. So n here is going to have to be whatever power we need in order for this to be truly equal. So right now, if I didn't put that 10 there, is my original number here, 2,500,000,000, is that really equal to 2.5? Well, obviously not. Put a dollar sign in front of both of those and there's a big difference. So what power of 10, remember powers of 10 will move the decimal when we multiply by them. So what power of 10 would move this decimal back to making this number? Well, if you think about it, 1 power of 10 would just get us to the end of the 5. But then I'd have a 25, and it would need to be followed then by 8 zeros. So once over, and then 8 more times to get my zeros, makes a total of 9 times it needs to move. So 2,500,000,000 is equal to 2.5 times 10 to the ninth power. All right, for our next example, ladies and gentlemen, we're going to go 602. And then we're going to follow that with 21 zeros. Now you might look at this number and think, all right, Mr. Burford, this just looks like it's too big. Are we just being excessive for the sake of example? And as much fun as that would be, no. No, we are not being excessive with our zeros just for the sake of example. This actually is a special number that comes up in chemistry. This is known as 1 mole. And it has a special meaning in chemistry. Particularly, it has to do with atomic mass and then mass in grams. So for example, if I had an element with an atomic mass, let's say of 53, if I had this many atoms of that atom, then I would have 53 grams of that element. So this is the number of atoms it takes for the atomic mass to turn into grams. So if this many atoms, then you have its atomic mass in grams. Well, ladies and gentlemen, this is a pain in the neck to write out. If you had to write a scientific paper and had to keep talking about this number here, but you weren't allowed to call it a mole, 1 mole, that becomes problematic. So I don't want to keep doing that. So scientific notation it is. So if we move that decimal over so we have just a single whole number digit, we're going to have to move it all the way over to right after the 6. So 6.02, and then just a bunch of zeros. So the zeros can go away, of course, except for that 0 between the 6 and the 2. We need that 1 to space out the 6 and the 2 into their proper spots. Now, times 10, and what power would we need here? Well, we would need 2 places to get to the end of the 2, followed by 21 places for all my zeros. So 2 and then 21 more makes 23. So 1 mole is 6.02 times 10 to the 23rd power. And this is why sometimes October 23rd is called Mole Day. 10 to the 23rd power, October 23rd. All right, ladies and gentlemen, for our next example, I'd like you to go ahead and write for me a 10, comma, and let's follow that by 12 zeros. So this time, I only have 1 digit that's not a 0, so that 1 digit is going to become my single digit whole number. That's going to become my coefficient, 1. 1 is my coefficient, times 10 to some power. Well, at this point, I've got the 1, I just need the zeros. So I need this 1 0 and then these 12 zeros, well that's a total of 13 zeros. Now you might look at this and say, hey, we can simplify this further. 1 times 10 to the 13th power would just be 10 to the 13th power. And while you're correct mathematically, that would not be scientific notation. Scientific notation will require us to keep this 1 because the 1 is the coefficient. So we do have to leave that there in scientific notation. You must have a coefficient, you must have a power of 10. All right, next example. 2.563. Well, conveniently here, we already have a single whole number digit. So my coefficient obviously is 2.563. But to turn this into scientific notation, I would need to multiply that by a power of 10. So remember, every time we use a power of 10, we are going to move the decimal. So ask yourself, how many times do you want to move the decimal here? Well, we don't want to move it at all. We want to move it 0 times. And so this would become 2.563 times 10 to the 0 power, because remember that 10 to the power of 0 really equals 1. So we're really just multiplying this number by 1. Now, ladies and gentlemen, you might look at this and say to yourself that this one doesn't really make sense in the real world. At least using it doesn't make sense in the real world. Mathematically, it's true, but it's not terribly useful, and you'd be absolutely correct. Scientific notation really was intended to be used with very large numbers, where the scientific notation is shorter than writing out the number itself. Here, where we find a number it's actually shorter to write the number than scientific notation, this really is not a time to use scientific notation. So while true, it is not a time we would typically use it. There is one other time that we do use scientific notation, ladies and gentlemen, and that's actually as we get really, really tiny. So what I'd like you to do is do 0 point, and then after the decimal, give me 7 zeros. 1, 2, 3, 4, 5, 6, 7. And then a 3, a 6, and an 8. So this is 0.00000000368. Now, when we get to numbers that are very tiny like this, and we see numbers like this, particularly when we're looking at atoms, when we're talking about the moles, atoms are very tiny. Okay, they're very tiny, and so you might have this when you're looking at things at the atomic level. So for numbers like this, even though they're very tiny, they're very long to write out because of all the zeros we've got to put in. So scientific notation, again, can be useful here. Now, right now, you might be tempted to say that we have a single whole number digit. And while you're sort of correct, we do have a single whole number digit. It doesn't count because our single whole number digit has to be something other than 0. The 1 has to be less than or equal to a, or to put it the other way around, a has to be greater than or equal to 1. So having a 0 as my first digit, not going to work. So if we slide the decimal over, still just zeros, just 0, 0, 0, 0, zeros, it'll have to slide all the way over here after the 3. So my coefficient this time is 3.68. 3.68. Then times 10, and well, how many times do we need to move the decimal? Well, I'd need to move the decimal once to get it to the other side of the 3, and then I'd have to move it 7 more times to get all those zeros. Well, once and then 7 more is 8. But the thing is here, moving the decimal this direction would make this smaller. So in order to make it smaller, we're going to make our exponent a negative. So this will be 3.68 times 10 to the negative 8th power. So using what we just discovered this time, let's go 0 point, and then I want to do 17 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, followed by a 2, 5. My coefficient then will require to move this decimal over to right there. So I get a 2.5 for my coefficient times 10 to the, well, I'd need to move the decimal once to get to the other side of the 2. And then remember there were 17 of these zeros after the decimal. So 1 and 17 makes a total of 18. Since we're making it itty bitty tiny, negative 18. So 2.5 times 10 to the negative 18th power. All right, next example. Let's try out 0.00000. That's 5 zeros after the decimal. 5 zeros after the decimal. 4.00506. So again, if I move that decimal over, boom, 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 it'll have to go right after the 4 in order to have a single whole number digit that's not 0. So 4 point, and now, well, what follows? 005, 06. That's my coefficient. Times 10 to the, well, it would take once to get to the other side of that 4, and then I need 5 zeros, so 1 and 5 makes a total of 6. 10 to the negative 6th power. 4.00506 times 10 to the negative 6th power is our answer. And so, ladies and gentlemen, just to think this through, make a little chart here. If you have a number and that number is greater than 10, greater than or equal to 10, then the power of 10 that you're going to use, n, is going to be greater than or equal to 1. In other words, n is positive. So if you have more than one whole number digit in your original, n will be positive. If you have just a single whole number digit, and here you'll recognize that this basically looks the same as the definition of A up top. Okay. In this case, n will be 0. And not only that, but our number is our coefficient, that's A. And so the number will equal A times 10 to the power of 0. Or itself times 10 to the power of 0. And then finally, if you have little things, now we're not going into the negatives here. So when we talk about little things, we're saying between 0 and 1. So really, 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 really tiny pieces. Not 0, not negative, but they're getting really tiny. In this case, n will be less than or equal to a negative 1. In other words, n is negative. So with all this being established, now we're going to actually get to kind of the heart of the lesson, which is using scientific notation. So in particular, we're going to be looking at multiplying and dividing numbers with scientific notation. Now, our coefficient times our power of 10 is one number written in scientific notation. So when we're multiplying them, we often write parentheses around them to say this coefficient goes with that power of 10. This is one number just written in scientific notation. So my second number here is 6 times 10 to the 10th power. So really, if you were to look at this and consider these scientific notation, you'd say, all right, how many numbers are we multiplying together? Well, really just 2. It's just 2 numbers being multiplied together. It's just that each number has 2 parts to it. So when it comes to actually multiplying them, multiply like parts. So I'm going to multiply my coefficient with my coefficient. 8 times 6 is 48. And I'll multiply my power of 10 with my power of 10. So 10 to the 7th power times 10 to the 10th power will become 10 to the 7 plus 10 power. Well, 7 plus 10 is 17. And ta-da! We've just multiplied 2 numbers in scientific notation. It's just too bad that our answer will be considered wrong. And maybe, ladies and gentlemen, you've spotted the problem. If we're multiplying 2 numbers in scientific notation, it would be fair to assume that we also want our answer in scientific notation, and that would be correct. We do want the answer in scientific notation, but scientific notation only allows there to be a single whole number digit. So my coefficient has to be between 1 and 10, including 1. So it can be anywhere between 1 and 10, but including 1. Well, this is obviously not fitting in that range. So what we need to do here then is we need to take our coefficient that's too big and kind of reimagine it. So 48 is really 4.8. So I move that decimal over, so there's only one whole number digit, 4. And then times 10, well, what power would you need to move an 8, or then move the decimal back over there to make a 48? Well, just once. So 48 was really 4.8 times 10 to the first power. So if I put this together then, my coefficient really is going to be 4.8. But then a 10 to the first and a 10 to the 17th will make a 10 to the 18th. All right, if we multiply, again, 2 times 10 to the 6th power times 9 times 10 to the 8th power. Again, multiply like things, so 2 times 9 is 18. 10 to the 6th times 10 to the 8th would be 10 to the 6th plus 8, or 14th power. Once more, if we kind of imagine this, I'm not going to do the red pen this time, but this would really be 1.8 as a coefficient, times 10 to the first would be what's needed to move that back. So first power to 14th power makes a total of a 15th power. All right, skip a few lines here, maybe about 3 or so lines, and we're going to do a division problem. Division we often write as fractions as we get closer to algebra, so I'm going to do this double big in a fraction. So 1.2 times 10 to the 2nd power, and I'm going to divide that by 3 times 10 to the 6th power. So similar to multiplication, we're going to divide like things. So here, 1.2 divided by 3, well, 3 goes into 12 4 times, so 3 must go into 1.2 0.4 times. A 10 to the 2nd power divided by 10 to the 6th power is going to be 10 to the 2 minus 6 power. Well, 2 minus 6 is negative 4. Negative 4. And similar to what we did last time, we're going to imagine this 0.4 then, which does not have a single whole number digit, in scientific notation. So if I were to move that decimal over once, I get a single whole number, but then times 10, well, what power would move that decimal back to the 0.4? A negative first. So when I combine these, I'm going to get a 4 from my coefficient, but then a negative 1 and a negative 4 will make 10 to the negative 5th power. Let's try another one. 6 times 10 to the 8th power over 8 times 10 to the 6th power. Now, we do prefer decimals rather than fractions here. Don't do fractions. So when I look at 6 over 8, think 6/8. Well, we know that reduces to 3/4, and we should have it memorized then that 3/4 is 0.75. And then times 10 to the 8 minus 6 power, so 10 to the 2nd power. If I finish this off then, I'm going to skip the red pen again. If we imagine scooting that decimal over, it'd be 7.5, but then how many times would we have to move the decimal to get it back to 0.75? Well, negative 1, because it'd make it smaller. So a negative 1 and a positive 2 combines to make a positive 1. And yes, just like the 1 coefficient, I would need a 1 exponent there for my scientific notation. 7.5 times 10 to the 1st power. That's what our answer would be in scientific notation. However, with numbers right around 0, like this, where it is 0, or numbers that are just close to 0, it often is going to be actually bigger to write them in scientific notation than to just write them normally in standard form. So if you consider this is a positive 1, so we're going to move this to make it bigger. If you move this decimal just 1 space to make this bigger, this really is just 75. So in reality, if we weren't required to write our answer in scientific notation, if we were actually doing this in science class, the answer to this problem I wouldn't bother writing in scientific notation. I would just write it as 75. However, the math of it, that's the scientific notation. And ladies and gentlemen, that is the end of this lesson.